discussions on the nonlinear activation units. The topic which we had in fact introduced in the last class, and also in this lecture I am going to introduce the learning mechanisms. And I think this aspect, that is learning mechanism, cannot be completed in this lecture alone. I think we are going to spill over again to the next lecture in order to complete the topic of learning mechanism. So we begin with the nonlinear activation units, and in fact what we are going to discuss in particular about the nonlinear activation units is also the aspect of stochastic neural networks, because whatever we have considered so far are all deterministic in nature. Now, as in the last class we were discussing about the nonlinear activation units. In fact, that's what we are needing very much for the realization or approximation of nonlinear functions. Okay, and typically that is what is going to be. So typically we are going to have for an output we are going to have a nonlinear approximation in the n-dimensional space. I mean, given a set of data points, given a set of observations, I mean that's what we are going to do. And for that we have to take some nonlinear activation unit, and we decided to take the sigmoidal function, okay, which is having the S kind of a shape, okay, as the activation function. So the thing which we had considered is a function somewhat like this, all right, and this function will be given by 1 plus exponential to the power minus AV, where what is the V? V is the input. I mean the input means that it is after the linear summer. That means to say that V is what we are obtaining here. Okay, we are calling it as Vk if this is the kth neuron in the system. And then what we are doing is to pass it through an activation function phi, and in fact this is one of the realization of this phi, that we can have it as 1 plus exponential to the power to the power minus AV. Okay, this means to say that when V tends to minus infinity, as you can very clearly see, that this phi function becomes equal to 0. Okay, and when V tends to plus infinity, okay, in that case we are going to have this term, that is exponential to the power minus AV, to be exponential to the power minus infinity, and that means to say that it is I mean the phi function value is going to be 1. So it is indeed bounded between 0 and 1. And what is this A? A in this case we consider to be a positive quantity, okay, and A basically determines the slope of this curve. Okay, in fact if we are making this I mean making A higher and higher, what's the limit that we are going to reach? That's right, that's right. I mean if we are making A very high, okay, then in a limit it reaches the threshold function. So it's the McCulloch-Pitts model that we are reaching if we are making A tending to infinity, and if we are making A tending to 0, okay, then that would mean that it's becoming a linear activation unit. Okay, so I mean this is in between the two, and this is I mean as I also discussed that it's going to be differentiable, it's going to be continuous, monotonically increasing. Okay, these are some of the characteristics that we can point out about this sigmoidal function. Okay, in fact this is not that it is the only realization of the sigmoidal function. The sigmoidal function in fact can be realized in, I mean using many functions. Okay, I mean something like this S-shaped characteristics it has to give. I mean not necessarily that the equation for that has to be 1 by 1 plus exponential to the power minus AV. It could be any realization. Okay, but yeah, I mean another advantage is the tuning of this slope of the curve using this A. All right, and now I mean we are going to see that just like the way sometimes we required I mean for the binary activation units, we had seen that we not only defined the threshold function or McCulloch-Pitts model, but we also considered the signum function where the activation values are finally restricted between +1 and -1. Okay. So likewise, we can think of a nonlinear function, okay, that ranges between -1 to +1. Okay. In fact, the best function for that is going to be, I mean, as a phi function, if we take the tan hyperbolic, if we consider the tan hyperbolic of AV, okay, then that is going to have a sigmoidal shape only, but it will range between -1 to +1. So it's characteristic, the tan hyperbolic AV. Again, in that case too, A is going to decide the slope of the curve, right? So it's going to be, I mean, like if this is -1, so on this axis we are plotting the phi function, and on this we are plotting the v function. It could be positive, v could be negative, and in fact when v is equal to 0, it's going to be 0, and in all other places, I mean, it's going to asymptotically reach -1 in this end, and if this is +1, then it's going to have a shape like this. So this is the realization of the tan hyperbolic activation function. Okay. So here the range is +1 to -1. Otherwise, shape-wise, it's very similar to what we had considered as a sigmoidal function realized using the exponential function like this, 1 by 1 plus exponential to the power -AV. So in fact, I mean, this function has got a name. This is often known as the logistic function. This realization 1 by 1 plus exponential to the power -AV, this is also known as the logistic function. Okay, whereas this is the typical tan hyperbolic function. Now the thing is that we now have a choice that we can use the activation units to be I mean, either McCulloch-Pitts model, that's to say a threshold function we can use. We can use linear activation units. We can use nonlinear activation units. Okay. The thing is that which of it we are going to use, that is again dependent upon several factors. In fact, what we sometimes do is that in a typical neural network, okay, which is realizable out of multiple layers, okay. In fact, we are going to talk more about that later on in this course, that where you can have one input layer, okay, from which the neurons are feeding their inputs, okay, and then we can have some output layer, I mean, at the end, okay, from which we are going to realize the final output functions, and in between the input layer and the output layer, we are going to consider several neurons, okay, which are only taking part in some intermediate computation, which are not exactly interfaced to either the input or the output. Okay. In fact, those are the neurons, or those layers we are going to define as the hidden layer, and typically in a neural network there could be one or more number of hidden layers. Okay, more about it we are going to see later on when we discuss the typical neural network structures, okay, especially the multi-layer feed-forward networks. When we see that time, we will be discussing about all these things. Okay. But I mean, what I try to say is that one could have a kind of a system where one can have the intermediate layer neurons, okay, which operate on the nonlinear activation units, because it's the intermediate layer neurons which ultimately realize the function that you are going to approximate, okay. And then finally at the end, you can combine, you can linearly combine the outputs which the intermediate neurons or the hidden layer neurons are generating, okay, and then we can realize the end function. So it could be a combination of the linear units, it could be a combination of linear threshold and the nonlinear activation unit realizable in the sigmoidal function, logistic function forms. So all these things are possible, and we are going to see that, okay, later on in our implementation. Okay. Now, another aspect, I mean, since we are discussing about the neuron models so far, okay, another aspect that we should discuss is that so far the neural network models that we have considered, they are all going to be deterministic in nature, right? Deterministic in the sense that, I mean, if you are feeding, okay, a fixed input, okay, like say for example, if this is the net activation V that we are going to feed, okay, from the linear input output, I mean from the linearizer output over here. If this is the V that we are going to feed, we are knowing that yes, the output is definitely going to be this, okay. I mean, in fact, if we are going to operate the neural network under different conditions, however, I mean whatever the conditions may be, okay, operating it under different conditions, still, I mean, whatever V you give, it will give the output as per the I mean function that you have realized out of it, okay. It is never going to act unpredictably, or it's never going to act that sometimes it's going to give you an output equal to this, or sometimes it's going to give an output equal to this for the same input, okay. But the neural network model could also be thought of as a stochastic model. In fact, that's how our biological neurons do behave. I mean there is a I mean psychophysical consideration. I mean people have conducted experiments and they have concluded that yes, I mean our biological neurons, okay, very often act, okay, as a stochastic model, okay. I think, I mean, in a very simplified form we can understand it like this, that is it that given a set of surroundings, okay, or if we are placed in some environment, is it that all the time we are going to act in the same manner? We are not, okay. I mean it could be that given the similar situations we sometimes act I mean in one particular way, and given the very similar situations or maybe exactly identical situation, we tend to behave in a little bit of different manner, okay. May not be I mean totally deviated from the manner in which we had acted earlier, but I mean maybe similar to it, but quite I mean different from what we did last time, okay. So it is a stochastic neural network model, okay. And in fact the way that you can think of as a stochastic neural model is like, so for example you take the Macaulay-Pitts model only, okay, where we are going to have the function as the I mean you can have the this is the V, okay, and this is going to be the phi of V, and in Macaulay-Pitts model we are going to have this to be 0, okay, and when V is greater than 0 we are going to have the value of phi V to be equal to 1, okay. Now it is I mean so far what we have learned is that as long as V is greater than or equal to 0, okay, we are going to have phi V equal to unity, and when V is less than 0 we are going to have phi V equal to 0. That's what we have learned, and it's always going to be true. Now with the stochastic model, we are going to define it this way, that phi V is going to be 1, okay. We can say that it's plus 1 with a probability PV, okay, and it's going to be 0 with a probability of 1 minus PV, okay. What does that mean? That we are going to define a probability, okay, that given that V is greater than equal to 0, okay, we are going to consider that phi V will be equal to plus 1, okay, with a probability PV. So it's not always true that given that V is greater than equal to 0, okay, it's going to have a value equal to unity, okay. It is probabilistic in nature. So that's what the stochastic model tells us, okay. And this probability is often defined this way, that we can consider the PV, the probability of activation, to be 1 by 1 plus exponential to the power minus V by T, okay. V we all know, okay, it's the same V that is the activation value, okay, and it is 1 by 1 plus exponential to the power minus v by t. The term t in this case is, I mean, a parameter, okay, that very much controls the probability, isn't it? You can just very clearly see it, that if we are having, let us say, if we take t is equal to 0, what's going to be the probability? In that case, the probability is going to be, I mean, this expression is going to be exponential to power minus infinity, so 0. So in that case, PV is going to be equal to 1. Okay, that means to say that it boils down to the deterministic Macaulay-Pitts model. Okay, because if we have that phi v is equal to plus 1 with a probability 1, that means to say that it's same as that of the Macaulay-Pitts model. And so, I mean, this way, I mean, we are going to have a more general form that Macaulay-Pitts model is going to be one special case, okay, where we put t is equal to 0. Okay, and if we keep on increasing the t, okay, let's say that we start increasing t from 0 onwards, okay, and we are going to reach higher and higher values of p. And what does it mean? That means to say that the network now deviates from its deterministic behavior and goes more towards a stochastic behavior. Okay, so as we keep on increasing t, the probability in fact decreases, okay, with the increase of t. Okay, now what this t is, I mean, so far I have deliberately told this as a parameter, okay, but people define this t to be a temperature. Okay, don't feel I mean surprised that we are relating the temperature to it. In fact, it is not the temperature, I mean the actual temperature of neurons or the temperature of our body, anything like that. Okay, this temperature is actually a pseudo temperature. Okay, in fact it is very similar to what we can define as a thermal noise model. Okay, in the sense that if we increase the pseudo temperature, okay, then the system behavior becomes noisy, and that is why its response is going to be probabilistic in nature. Okay, so this t is defined as a pseudo temperature, and at t is equal to 0, okay, it is noise free, so it is absolutely deterministic in nature, and with increase of t it is going to be more noisy in its behavior, and there the stochastic model is coming in. So these are the things that I wanted to tell you in connection with the neuron activation unit. So we learnt about the threshold units, we learnt about the linear units, we learnt about the nonlinear activation units, and now the stochastic neural network models. Okay, in fact all these things will be needed for us as we progress more through the lectures. Okay, and is there any question regarding this topic of the neuron models in general? I mean, be it linear, non-linear, whatever. Okay, whatever we have discussed. Okay, is there any question? Okay, so in that case we can proceed to the next topic for us. Okay, which is the learning model. Okay, so we are going to consider the learning mechanisms in neural network. Now, something about the learning we can intuitively know, okay, because we all go through the process of learning, okay, when we are transformed from a child to an adult, okay. We go through the process of learning every day, every moment, in fact. Okay, and we know what it is, but it's a very similar kind of a learning mechanism that we have to think of for the artificial neural network models also, because ultimate objective is that, the reason why we picked up artificial neural networks topic is that we can mimic what goes on, okay, mimic in a very rundown version, okay, certainly not the exact realization of the human brain, okay, but we can just mimic it in a smaller scale in order to incorporate the learning mechanism into it. So, what it I mean, what are the essential components of learning? Okay, these things we can list out. Okay, first is that for any learning to take place, okay, we give a stimulation. Okay, there is a set of stimulations that we are receiving from the input, okay, from the environment. Okay, and what we are doing after obtaining the stimulations is that, okay, we are making changes in the free parameter. So, changes in the free parameters of the neural network. Okay. In the case of biological neuron, it is the synapses, okay, that is going to change, okay, the synaptic behavior or the synaptic connection strengths which adapts, okay, according to the stimulation that we receive. Okay. And in the case of the artificial neurons, okay, which we had already seen, okay, when we were discussing about the linear neurons, we had seen that dependent upon the error that we are going to make, okay, between the actual and the desired response, okay, that combined error function, and then we are going to adjust the WIJs, that is to say the synaptic weight connections, okay, in accordance with the error that we are making, or we are proceeding in the direction of gradient descent, and then we are adjusting its parameters. In fact, the parameters that we adjust, by free parameters we define the synaptic weights and also the bias, or the weight that is associated with the bias. I mean, the model that we chose there, all the free parameters are these synaptic weights and bias that we are going to adjust. And then when these changes have been done, in fact, we do it in an interactive way, meaning that we make changes in the free parameter, then again we see that how much we have deviated from the actual, then again we change. Okay, it's an iterative process that goes on, and it takes, in fact, several iterations. Okay, but we go through the process of learning, and once it is learned, okay, then what it does is that it responds, okay, to the environment in a changed way. I mean, so it responds in a new way. Okay, that's what we can tell about it. So these three are the essential components about the learning. That's to say, you have to get the stimulation, and what is most important is that you have to make changes in the free parameters of the system. Okay, and then once those are changed, then it responds in a new way. Okay, meaning that now it is in a position to accept the kind of inputs or patterns which it hasn't encountered before. That means to say that it is in a position to accept the test patterns, and then dependent upon the test patterns, it is going to give you the outputs. I mean, a correct classification or a correct response it's going to give, because it's already already it has adjusted its free parameter in accordance with the stimulation that it has received from the environment. Okay. Now, there are some basic learning rules, okay, which we are going to consider. In fact, we can list out 5 basic learning rules. Okay, and we can list them out as follows. That at first we can list out, which is very important, that is the error correction learning. Okay, we will come back to each of these in a more detailed way, but first let me list out the 5 basic learning rules. The second that we are going to consider is the memory based learning. The third category is the Hebbian learning. The fourth category is competitive learning. And the fifth and the final category is Boltzmann learning. Okay, and we are now going to take each of these categories, okay, each of these basic learning rules, okay, in a I mean one by one we are going to consider that. Okay, so what is, after all, the error correcting, or this first one, that is error correction learning? I think we have already seen about it, okay. In the last lecture we had seen the error correction learning, okay, because essentially what we did was that we took the error, okay, let's say that the error EK, okay, that's the error, okay, and we are going to write it as DK, or I think we might have put the notation as TK, that's target, or D you can call it as desired, minus YK. And in fact, a more customary way of writing this type of expression is that we put in parenthesis the, I mean, as this n. And what does this n mean? This n indicates the discrete time step. So n is the discrete time step. In fact, you can imagine that this is the number of iterations that is taking place, because what we are doing is that we are finding out the error, we are adjusting the synaptic weights, okay, and then after the adjustment is done, we are again going through through the error computation, okay, again adjusting the synaptic weights, and these things we are doing iteratively. So this n is the iteration number, or we are calling it as a discrete time step. Discrete time step in the sense that in one time step, I mean, like if say we take n is equal to 1, that means to say that in that time step, okay, whatever things are being done will be written, okay, and then the next time step will be recognized as the time step 2 when we will be doing the second iteration. Okay, so this is the error expression that we had considered, and then ultimately what we had thought of is the minimization of this En. Okay, this is the error, okay, that we wanted to minimize, the sum total of error, and that was nothing but summation of EKN square, because we are going to have different units, okay, and this is the kth unit that we consider, and we have to sum it up, okay. So this is E square Kn, okay, and then we had in fact derived this in the last class, that the change of weight that is going to take place, which we can write as Wkj, okay. So Wkj for the discrete time step n is going to be what? Remember? Eta being the learning rate, okay. Then Ek, that's the error term, okay. Ekn we are going to write multiplied by input, which is going to be xj of n, okay. So this is the rule, the weight updating rule that we had discussed, okay. This is in fact based on the gradient descent, okay. We had derived that yesterday from the gradient descent consideration, okay. And in fact this rule is also often called in the literature as the delta rule, or it's also known as Woodrow-Hoff rule, okay. So different books or journals, okay, could be just calling these function, okay, calling this equation as either gradient descent or delta rule or Woodrow-Hoff rule, whatever name they may say, okay, but ultimately it means that this is the adjustment or the increment in the weight that you are going to do, okay. And then the updated synaptic weight that we are going to get is that based on this delta Wkj, the Wkj is going to be updated. So we are going to say that Wkj at the step n minus 1, at the time step n minus 1, should be equal to the Wkj which we had in the time step n, okay, plus this delta wkj at the time step n. Okay. So, this is going to be the updated synaptic weight. Okay. So, this is the simplest form of the what we had discussed as the first category, that is the error correction learning. Okay. And the next one we are going to consider is the memory based learning. Okay. This is what we are going to consider now. Okay. As a matter of fact, I mean, if you are asking me that which is the one that the human brain really follows, which kind of learning mechanism, okay, in fact, it's very difficult to say. I mean, it's such a complex process, and I don't think that so far people have understood it in the I mean exactly correct way, okay, because it is seen that, I mean, from different experiments people concluded that the learning mechanisms, okay, they are different under different conditions, okay, and it is thought that, okay, sometimes we do the learning in this manner, sometimes we do memory based, sometimes we do Hebbian learning. All these things are I mean essentially biologically motivated. So, the human brain in fact have been doing, I mean have been adopting this kind of, I mean all these kind of learning mechanisms in some way or the other. Okay. Now, for the case of the memory based learning, what we are doing is that we store or rather memorize, okay, a set of patterns. Okay. Let us say that when we are considering a network, okay, let us say that we have a network with n different inputs, supposing n, okay, and here we have the inputs 1, 2, 3. In fact, the input will be normally called as the x1, x2, x3 like that, okay. I mean, so these are the input numbers, I am saying 1, 2, 3 up to n, okay, and these are going to the linearizer, activation unit and all that, okay. But what I mean to say is that this n, okay, or let's not okay, let's call this as m, okay, m different inputs we say. So, x1 to xm are going to be a set of inputs, okay, and for that we are going to get some output, okay, and that output is going to be the output y, okay. Ultimately we are going to get a y for this set of inputs. Again we take a different pattern, we take a different x1 to xm, okay, and we get a different output. In fact, in the learning mechanism what we do is that for the memory based learning, that we try to memorize, okay, the input vector, the association between the input vector and the output, okay, the desired output, I mean to say. That means to say that you are feeding a set of values as input that defines a pattern. So, the pattern, when I say a pattern, that pattern is consisting of x1, x2, x3 up to xm, okay. So, this pattern in fact mathematically, or I mean expression wise, we can call it as a vector. So, we are in fact feeding a x vector. So, when I say that I am feeding x vector, that means to say that I am feeding this input, okay, and for an x vector, okay, we are obtaining a desired output, that is d, okay. Now, if I have multiple such output units, okay, then even d is also going to be a vector, okay, but without loss of generality, I mean I can consider the case of a single neuron as an output, okay, and its response I am calling as d, okay. In fact, d could be a vector, d could be a scalar, but just without loss of generality I am considering d to be a scalar quantity, right. So D assumes some value. I mean, associated with this pattern X vector, we are going to have D as the desired response. Now, for a system behavior, okay, we might have decided to store, let's say, n such patterns. Okay. So that means to say that I am having a set of this X vectors, and I call this as Xi, okay, and I is equal to 1 to n. Okay. So this n indicates what? The total number of patterns that we are going to feed to the system. Okay. And for every pattern or every vector, every input vector Xi, we are going to get a desired response which is going to be Di. So Xi will be associated with one Di. Xi is a vector giving the inputs and Di is the desired output of it. So we are going to have an association between this Xi and Di, and again this will be for I is equal to 1 to n, right. So in a memory, okay, we are in a large memory, we are going to store all these patterns, okay, which we memorize. Now the thing is that when we are presented with a pattern that we haven't encountered before, that supposing we take this system, okay, to an unknown environment, okay, but I mean unknown environment in the sense that I mean unknown vector that we are obtaining, but yes, environment is going to be the same because I mean it has been trained with some environment only and it has received the inputs from a very similar environment, but we have got a, let's say, new test pattern X test, okay, X test vector that we are feeding as an input to this system, and this X test is not any one out of this set of Xi's, okay. And what we are going to find out is that when we give this X test as a vector input, okay, then what is going to be the corresponding output to it, okay. That's the question that we are going to ask. So if the learning is proper, so here the learning is based on memory. So what it does is that it now finds out, okay, from the memory that which of these vectors is going to be closest to this X test, okay. Closest in what manner? Naturally, we have to adopt some distance measure, and the simplest of distance measure that we can think of is the Euclidean distance. This is in fact all these X vectors are essentially m dimensional vectors because we are considering m different inputs to the system. So it is m dimensional vectors, and we are going to find out the Euclidean distances between the X test and each one of these Xi's which are already stored in our system. So we are going to examine that if X test is closer to X1 or X2 or X3 up to Xn, okay, and the one that is closest to, okay, let us say that Xk happens to be or Xj happens to be the closest, okay. So we can say that out of these vectors, okay, if we are able to find out, okay, a vector Xn prime, let's say, okay, where Xn prime essentially belongs to this set, the set of X1, X2, etc. up to Xn for n different vectors or n different patterns, okay. We can say that this Xn prime is the nearest neighbor of X test all right, if the minimum of the Euclidean distance between Xi and X test, okay, and the minimum is searched over the I space, that is varying I from 1 to n. Okay. And this is the minimum of all these d's happen to be the d between xn prime and x test. If it fulfills the condition, then we are going to say that xn prime is going to be the nearest member of this x test. Okay, is this clear? I mean, it's one and the same as telling in a very simple language that, I mean, the minimum of Euclidean distance that we are getting out of this set of x1 to xn. Okay, in fact, it is just a simple mathematical representation of that, that you take the minimum of this distance, Euclidean distance between xi and x test, and this minimum you find out over the I space, and then if that happens to be xn prime x test, okay, then xn prime, okay, which belongs to this is going to be the nearest neighbor to this x test. Okay. So, then what we are going to do? We have found out the xn prime. So, then the corresponding dn prime, which is the response, okay, then that is going to be the response that we are going to consider for x test. Is that understood? Okay. Let me give you a very simple example. Okay. That supposing we have got different patterns, okay, and ultimately we are going to classify the input patterns into one of two classes. Let us say that the classes are such that some of the patterns we are going to call as the pattern 0, means binary pattern classification problem. So, some of the patterns we are going to classify as the class 0, and some of the patterns we are going to call as the class 1 patterns. Okay. And let us say that I mean, we have got all this set of observations, isn't it, which we have stored in the memory. And let us say that we just plot it in some space, okay, a space containing all these I mean inputs, and let us say that for one particular pattern, okay, we have got the classification 1 here, classification 1 here, classification 1 here. So, these are all the positions of the vectors. Okay. So, for this position of the vector the output is 1, this position the output is 1, this position is 1, maybe for this position the output is 0, maybe for this position the output is 0, maybe for this position the output is 0. Okay. So, like this I have got many observations. So, for some we have put it into the 1 class, and for some we have put it into the 0 class. Okay. This is what we memorize, and now a test vector is presented to the system, and that test vector supposing is this position. Okay. Now, what the nearest neighbor criteria really tells us, or the memory based learning tells us, is that at this position it is going to find out that which is the nearest neighbor. Okay. Supposing if the nearest neighbor is this one, okay, then we find out, I mean, if after performing this test, that is determining the nearest neighbor, we find that this one happens to be the nearest neighbor, then we are going to adopt this class to x test. Is that understood? So, that means to say that in that case we are going to classify this. I am just writing it with a different pen just to indicate that it is a test. So, all these black ones are the training patterns, or the patterns which have been memorized already, which are already there in the memory, and this is a test pattern that we have presented, and the test pattern will now be classified as 0. If in this region we present a test pattern, that will be classified as 1, because its nearest neighbor is going to be having a classification equal to 1. All right. Now, I mean, it is quite logical, isn't it? I mean, I do not think that there is any reason to mistrust this approach. Okay. But if we analyze it very closely, okay, we can follow, I mean, we can just have some flaws. You see, after all these classifications of zeros and ones, how have we done? We have done it based on some observations, and I mean our observations may be 99% correct, but it may be 1% of time the observation may be going wrong also. What I mean to say is that it could be that in the pattern association process, or when we are putting it into the memory, we have put, let us say, all these regions are having responses of zeros, and one of these has got 1, and then these things are all 1s. Okay. Some response like this, where this 1 that has come up, okay, is indeed one of our wrong observations, isn't it? Or we can call this 1 to be an outlier. So this is an outlier, okay, in our pattern presentation process. Okay, so when we are presenting this x1 to xn, there itself we have got one outlier, okay, which is lying over here. But whenever we are training the system, whenever we are putting into the memory, we are not really finding out very closely that whether we have got a correct pattern or whether we have got an outlier. We accept everything as it is. Now, just imagine that we are presenting a test vector, and supposing the test vector happens to be placed over here. If we adopt the nearest neighbor criteria, in that case, what is going to be the nearest neighbor of that? That outlier can act now as a nearest neighbor to x test vector, and in that case the classification that this x test vector is going to get is 1, which is not a very correct classification, because we are making the classification based on an observation, based on an earlier observation, which is already wrong, which is already an outlier, and it will then be categorized into the outlier, which is not correct. Okay. So naturally this approach of finding the nearest neighbor has got some problem. So what are we going to do? We should find out a variant of this method. Now, any suggestion that can come from you people?
So we find out nearest neighbors.
Correct. It's very correct. I mean, as one of your friends pointed out, that it's going to consider the neighbors, not neighbor. Okay. So that plural itself means that I mean the answer that your friend has given is quite correct. In fact, if this is the position where we are going to have the x test vector, okay, we are going to define a neighborhood. We are going to define a neighborhood around which we are going to consider that in that neighborhood what are the different xn's that are available. We are going to observe the xn's in this neighborhood, okay, and in this neighborhood if we find out that I mean majority of those are going to be zeros, like this is the case, that supposing the nearest neighborhood is like this, okay, then we find out that out of all these nearest neighbor classes, okay, which is the one that is more predominant. In this case it is 0. So in that case we are going to classify this S test vector as the class 0. Okay. So in that case the outlier is not going to play any significant role, because the outlier will be outnumbered by the correct classes. All right. So in fact I mean this kind of an extension to this idea is called as the k nearest neighbor classification. And what is meant by k nearest neighbor is that we are not going to consider one neighbor, we are going to consider k different neighbors, okay, and it is the best out of the k nearest neighbor that we are I mean it is I mean out of the k nearest neighbors, okay, we are going to consult its I mean D's. So, we are going to consider the I mean the values of the outputs, okay, which are there for the nearest neighbors, and then depending upon the majority choice, okay, majority output, we are going to decide that what is going to be the response to this X test. So, for X test we are going to find out the best value of D, okay, by considering the nearest neighborhood. You can take 3 nearest neighborhood, 4 nearest neighborhood, like that, in which case it means to say that you consider not the nearest neighbor alone, but 3 or 4 nearest neighbors, or defining a nearest neighborhood zone, okay, and then ultimately classifying it. So, this is the basic philosophy behind the second learning rule, okay. I mean out of the 5, this is the second one that we have considered so far, okay. And now we can come to the next learning mechanism, which is called as the Hebbian learning, okay. In fact, Hebbian learning, I mean it is thought that Hebbian learning is the one that is closest to our biological neuron learning mechanism, okay. In fact, all these theories, okay, basically originated from Hebb, okay. In fact, Hebb is a neurophysiologist, okay, who in the year 1949, okay, he came up with a book, okay, which is called as the Organization of Behavior. Okay. In this book of Organization of Behavior, Hebb has in fact proposed the kind of model, okay, that possibly our human brain neurons, okay, adopt, okay. All that it says is that supposing we have got a neuron cell that is A, and we have got another neuron cell that is B, and this cell A and cell B, they are connected to each other using a synaptic weight, right. So, what Hebb says is that if the cell A happens to fire the cell B, fire means if cell A is cell A's activation at a given time can activate the cell B, okay, in that case the metabolism, I mean the metabolic changes that happen should be such that A's efficiency in firing B increases, okay. So, all that it says is that if the cell A, if cell A consistently fires the cell B, okay, then metabolic changes happen so that the efficiency of A firing B increases, means whatever happens. So, if cell A fires cell B, in that case the synaptic weight will be so increased that next time the cell A has got a better probability of firing the cell B, okay. And I mean I am not writing the reverse of that, the reverse of that is also true. I mean if cell A does not fire cell B, okay, in that case that synaptic weight or that synaptic connection should be weakened, okay. The metabolic changes will be such that that synaptic connection will be weakened, and ultimately the synaptic connection could be lost also, okay. So, I mean, this is, I mean, quite an interesting thing that Hebb had proposed. Okay, in fact, all that it means is that whatever behavior happens, okay, with I mean the behavior being cell A firing cell B, okay, that is supported. Okay, so that next time you have got a better possibility of doing it. Now, this postulate of Hebb, okay, could be very easily translated into our neural network mechanism also. In what manner? In that case, we can say that I mean we can define a presynaptic neuron and we can also define a postsynaptic synaptic neuron. So, the presynaptic and the postsynaptic neurons, they are connected to each other using the synaptic weight. So, that means to say that if we observe that the presynaptic neuron and the postsynaptic neuron, they are both activated at the same time step. I mean at the time step n, if we find that the presynaptic neuron and the postsynaptic neuron both have got activated, okay, in that case we are going to increase the strength of this WKG. And if the reverse of that happen, that if cell A and cell B, they are activated asynchronously, means not in the same time step. Okay. If this happens in N and the activation of B happens in a different time step, or rather to say in time step N, if I say that cell A is activated but not cell B, or vice versa, in that case we are going to reduce the strength of this WKG. All right. So, that is the way it is being adopted into the artificial neural network behaviors also. Okay. So, we are going to consider some details about the Hebbian learning mechanism and the other aspects of learning in the coming lecture. All right. Thank you very much.